Hello class, this is your Chapter 12 lecture on hormones, physical activity, and exercise training. To start off with the chapter objectives, I know that this is a little bit shorter of objectives list than we've had before, but I don't want you to get overwhelmed by it. So I do want to specifically go down some of these objectives. I know normally I say read them on your own, but I do want to point out the ones that you should comprehend and understand by the end of the lecture, or at least after you've read the book, you've taken notes, you've done your homework exercises, and hopefully also after hearing the lecture today. So maybe not necessarily draw and label the body's endocrine glands, but definitely be able to be shown a picture, and you should be able to point out the different endocrine glands and their anatomical locations. And you'll actually see that in a slide here in just a moment. I do want you to be able to describe how hormones alter cellular reaction rates of specific target cells. I do want you to understand how hormonal, humoral, and neural factors stimulate endocrine glands. We are going to talk extensively about the anterior and posterior pituitary glands that's attached to the hypothalamus, in addition to the acute and chronic physical activity, how that affects their release. So you might want to kind of star that one, highlight that one. That is kind of the point of the chapter. We are going to go over the thyroid gland hormones, the functions, and again, acute and chronic physical activity, how that impacts their release. And then also the adrenal medulla and the adrenal cortex hormones. Again, same concept, know what their functions are and how acute and chronic physical activity affect their release. So if you notice, the last 3 bullet points of this objective is talking about specific endocrine glands that you need to be aware of. So again, the anterior and posterior pituitary glands on the hypothalamus, the thyroid and the adrenal medulla, and the adrenal cortex hormones. Most of the second slide of objectives talks to us about understanding the difference between type 1 and type 2 diabetes mellitus. This is a really good lecture for anyone that is listening today that doesn't understand what diabetes is, why it's considered kind of a disease that's associated with metabolic conditions. And it gives you kind of a good overall understanding of the difference between type 1 and type 2, who it affects, when typical onset is, and how it actually affects individuals. So on this particular slide, we'll define the different types. You'll list some of the risk factors. That also will help you as a professional identify, maybe based on some symptoms that your client is reporting to you. I hope you guys will understand the benefits of regular physical activity for a type 2 diabetic. And then we also need to discuss training effects on endocrine function itself. This is a picture pulled directly out of your textbook. It is your endocrine system, the glands, and their hormones. So a couple points that I want to highlight with you. We're going to be talking extensively about the pituitary gland and the hypothalamus. That was one of your objectives. The hypothalamus is attached to kind of the inferior portion of the brain, or the bottom or the lower portion of the brain, and the pituitary is actually attached even lower than that right here. So you can see all these different types of hormones that are released from this particular location on the brain. And it's located right here. It's actually a little bit larger than what is shown here, but you can see in relation to the other organs that we're going to be talking about, it is pretty small in nature, but it has a lot of hormones that come from it, and so that's one of the reasons that we focus a lot on the hypothalamus and the pituitary gland. Going down then, here's your thyroid and parathyroid glands. You'll see another picture of these. The parathyroid glands actually look like little yellow jelly beans. But this has a lot to do with so thyroxine, why do I even try and say T2 and T3 is what you commonly refer to the hormones that come from the thyroid gland. This is typically the gland where people will say, oh, I have thyroid issues, that's why I'm very overweight. When in actuality, research has shown that only about 3% of the population really suffers from either a hyper or hypoactive thyroid, thus affecting their weight loss or weight gain. So just kind of keep that little piece of research tidbit in the back of your mind. If anyone says, oh, I have a thyroid issue, they may or may not have seen a doctor that has diagnosed them with that kind of situation. So the pituitary gland, again in the brain, the parathyroid and the thyroid gland here is very important. Here's your thymus gland. We'll be talking a little bit about that because of the intergluten factors, the IGF-1 that's important in regards to muscles. The heart is important because it is the actual pump that sends these hormones through the circulatory system to reach the cells. It does not produce any sort of hormones. It is simply responsible for the transport. We'll talk a little bit about the stomach, the duodenum, and the jejunum. We'll talk extensively about the adrenal gland, specifically the adrenal cortex and the adrenal medulla. So you can see those pictures just kind of brought out over here. The cortex is actually the outer layer of this hat that's present on the kidneys. The medulla is actually inside the adrenal glands itself. And if you remember us talking about epinephrine, norepinephrine, that's what's produced in the adrenal medulla here. And we know those are two very important hormones when it comes to excitation, especially that fight or flight mechanism that our body produces when there's an emergency. Kidneys are very important. Oh, I lost my cursor. There it is. We'll talk about erythropoietin. I've actually included some videos for you on the course shell, because EPO, it's also referred to as EPO, is how Lance Armstrong and many cyclists within the Tour de France performed blood doping in order to perform those great feats that they did, cycling for hours upon end, going through the French Alps and the French mountains. So if you're interested in learning more about erythropoietin, we will talk about a little bit later. But again, there are two good videos. They're short, only about a minute each, that explains what erythropoietin is, how it's created in the kidney, and what exactly its function is in assisting an endurance athlete last longer and be able to endure hours of their sport. And then also we'll kind of end talking about the the ovaries and the testes. We know that different hormones are presented there, obviously with estrogen, progesterone with the ovaries, and testosterone and androsterone from the testes. So this is a good overview, ladies and gentlemen, to go back to this very first bullet point, to be able to locate the endocrine glands and their anatomical functions or locations, kind of be aware of this picture. All right, so moving on. The endocrine system consists of a host organ or gland, minute quantities of hormone chemical messengers, and then a target or a receptor organ. So the system integrates and regulates body functions to stabilize the internal environment. Endocrine gland hormones affect all aspects of human function. They regulate growth, metabolism, and reproduction, with heightened acute and chronic response to physical and psychological stress. Hormones maintain internal homeostasis by modulating electrolyte and acid-base balance, and also adjust energy metabolism to power all forms of human biologic work. The endocrine system operates in synchrony with the nervous system to provide hormonal secretions as needed throughout the body. So these endocrine hormones serve as chemical messengers in the bloodstream, and that's why I pointed out for the anatomical locations of the endocrine glands, that's why I pointed out the heart, is because the hormones are transported through the bloodstream, jettisoned and pumped by the heart, and then the nervous system serves as the electrical conduit system. The nervous system essentially performs instantaneously with short-lived results. The endocrine system hormones act relatively more slowly and usually have longer lasting effects. So this particular chapter is going to review the important aspects of the endocrine system, including its functions during rest, as well as physical activity and response to acute and chronic exertion. There are three components that characterize the endocrine system: a host gland, hormones, and then a target or a receptor cell or organs themselves. Glands classify as endocrine, exocrine, or both. Endocrine glands secrete hormones, and they lack ducts. So in other words, they discharge their substances directly into extracellular space surrounding the gland. And if you look in your book, figure 12.2 illustrates how hormones diffuse into the blood for transport to target tissues throughout the body. What exactly makes a chemical a hormone? The term hormone was coined from the Greek word meaning impetus. An accepted operational definition describes a hormone as a chemical, usually a peptide or a steroid secreted by a cell or group of cells into blood for transport to a distant target, where it then exerts its effect at a relatively low concentrations. Research findings suggest this may be too broad of a definition because many different non-hormone substances also function as chemical messengers. Do they have to be transported to distant targets? Physiologists have actually questioned whether a chemical must be transported to a distant target to classify as a hormone. For example, one hormone secretion can trigger the release of another hormone with a different function. For example, luteinizing hormone acts on Leydig cells in the testes to stimulate testosterone production. And there's a couple of other examples of this situation. So the research is still kind of out there in regards to, does it have to actually transport through the bloodstream? However, right now most of the hormones actually do. So you can see on the slide the hormone classifications. They typically classify according to several different systems, their sources, their receptor type, or their chemical structure, which represents the most common classification scheme that you see here. So we typically go by 3 different chemical structures in which hormones exist. The first is the peptide or the protein hormones, which are composed of linked amino acids. Amine hormones are derived from a single type amino acid, and then steroid hormones are actually derived from cholesterol as well as amine hormones. So that's kind of the reason why I left that to the end. So you can see here that the peptide hormones excuse me, typically bind to the surface membrane receptors and then act through a second messenger. Steroid hormones usually come from cholesterol, usually only are produced by the adrenal cortex, the gonads, or the placenta. And then the amine hormones that we talked about a little bit earlier are examples of epinephrine, norepinephrine, as well as serotonin. This is a good example for you guys. It kind of classifies the different hormone types and gives you examples, tell you how it's synthesized and stored, where it's released from, or the manner in which it was released from the parent cell. The transport medium, if you'll notice, most of the transport medium is through the bloodstream. It'll tell you if it's got a short or long half-life or lifespan, where the receptor location is, whether it's on the cell membrane or actually inside the cell in the cytoplasm, maybe even the nucleus of the cell. The response to the receptor ligand binding and the general target response. So just be aware of these different classifications and how they react, their lifespan, things of that nature. Most hormones do not directly affect cellular activity. Rather, they combine with a specific receptor molecule on a cell surface. The cell then discharges a second chemical that initiates a cascade of cellular events. Figure 12.3 schematically shows a non-steroid hormone, which is displayed as a triangle. Let me speed up for you guys. Here we go. The non-steroid hormone, which is the triangle that you see right over here in the extracellular space, as it binds to its receptor and then penetrates the intracellular space through the phospholipid bilayer that you can see right here. The binding hormone acts as a first messenger to react with the enzyme adenyl cyclase in the plasma membrane to form cyclic 3,5-adenosine monophosphate. So this is our cyclic AMP. This compound then acts as a second messenger mediator, and it influences cellular function by initiating a predictable series of actions within the target cell by one of the 4 mechanisms listed. It either changes the intracellular protein synthesis rate, it alters enzyme activity rate, it modifies cell membrane transport, or it influences secretory activity. It's important to understand a target cell's response to a hormone depends on specific protein receptors on its membrane or in its interior. So I'm going to say that one more time because that is important to understand in regards to how hormones function. A target cell response to a hormone depends on specific protein receptors on its membrane or in its interior. So these are the mechanisms that we kind of talked about a second ago in how hormones influence cellular function. And there's also 3 factors that determine a hormone's plasma concentration. It is either the sum of the synthesis and the release by the host gland, rate of the receptor tissue uptake, or rate of removal from the blood by the liver and the kidneys. In most cases, the hormone removal rate, which is usually quantified in the urine, equals a release rate. So again, this is another visual that kind of gives you a good idea of how hormones function within the body. So you can see here at the top of the screen, you've got your brain. The bottom portion of the brain, you've got the hypothalamus, which the pituitary gland is attached to. So we have our anterior and posterior pituitary gland that is excreting a certain hormone, and we see here, very important, that it travels through the bloodstream. So the triangle represents the hormone that was released by the pituitary gland. It travels through the bloodstream. This particular hormone that's being excreted is traveling to the kidney itself, which is binding with certain receptor sites on the phospholipid bilayer of the cell itself. And so that's what you can see here, kind of that lock and key mechanism. So the hormones secreted from the endocrine glands, they travel via bloodstream in order to exert influence on different body tissues. So different hormones are targeting different glands within the body itself. And again, in regards to the target cell activation, it really depends on the hormone receptor interaction and 3 different factors that are present. Again, blood levels of a specific hormone, in other words, how much is actually present within the blood, relative number of target cell receptors for that hormone. So if there are only a few receptors that are present, there's not a lot of opportunity for those hormones to bind. And it also depends on the affinity or the strength of the union between the hormone and the receptor. So when that hormone actually reaches the receptor site, how strong is that union? Is it a good lock and key, or are there small imperfections at the receptor site that would cause the hormone to not be able to bind? How do they affect enzymes? Alteration of enzymatic activity and enzyme-mediated membrane transport constitute the major mechanisms of hormone action, and they affect enzyme activity in one of 3 ways. They can stimulate enzyme synthesis. They can also combine with the enzyme to change its shape through allosteric modulation, and this increases or can also decrease an enzyme's ability to interact with the substrate. And it can also activate many inactive enzyme forms to increase total enzyme activity. In addition to altering enzyme activity, hormones either facilitate or inhibit transport of substances into a cell. Insulin, for example, promotes glucose uptake through the cell's plasma membrane. In contrast, the hormone epinephrine inhibits the cell's glucose uptake. Hormonal, humoral, or neural mechanisms stimulate endocrine gland function. Each of these stimulation methods functions as a reflex pathway, singly or in combination, to ultimately trigger and regulate a specific hormone secretion. All reflex pathways exhibit 5 similar components. And they are stimulus, input signal, signal integration, output signal, and then a response. In endocrine reflexes, the output signal represents the hormone or neurohormone. Hormones often influence other hormone secretions. For example, hormones from hypothalamic trophic releasing and inhibiting hormones induce discharge of most anterior pituitary hormones. The anterior pituitary hormones, in turn, then stimulate other target gland exocrine organs to release their hormones into the circulation. Increased blood levels of these hormones provide feedback to inhibit release of the anterior pituitary hormones, which ultimately inhibits target gland secretion. So how do you control or turn off hormone release? It's called the negative feedback system that actually turns off hormones. So in this example that you see here, an increase in blood glucose concentration following a meal initiates insulin secretion. So when you eat a cheeseburger, a slice of pizza, or heaven forbid, maybe a healthy turkey sandwich, our body reacts to increase the glucose concentration in order to increase the insulin secretion. So what happens is we eat the sandwich, our blood glucose levels goes up because of the macronutrients that are present within that particular food item, and our body responds by producing insulin. Insulin then travels to the blood to the target tissues to increase glucose uptake and increase the metabolism as well. The resultant decrease in blood glucose concentration provides this negative feedback signal that turns off the reflex, ending in insulin's further release. So you can see that illustrated for you here. Generally healthy meal, and because of that consumption, our blood glucose levels goes up, and when our body detects that we have increased circulating blood glucose, we respond through the pancreas by activating insulin production. And the insulin is what takes that glucose to get it into the actual cell itself. And this is why we're talking about diabetes, because this is an issue for individuals suffering from type 1 or type 2 diabetes, because our pancreas cannot appropriately respond to produce either any insulin or enough insulin to aid this process in occurring of taking glucose into the cell. And that's what insulin in our body is produced to do, is to be kind of that crossing guard, to be kind of that helping hand to aid glucose and get into the cell. Without insulin, glucose can't physically get into the cell, and that's got some major repercussions when it comes to being ready to perform any sort of physical activity or movement in general. So again, this is the negative feedback loop. And once the glucose has been inserted into the cell with the assistance of the insulin, our glucose levels in the blood go down, and that is also read by our body, which means that we begin to stop in the production of insulin because we no longer need it at that time. Before we talk about skeletal muscle as an endocrine organ itself, I want to back up for a second and talk about hormone-to-hormone interactions, because it's very possible that there are multiple hormones present at the same time to control different cells and tissues. There are three types of interactions of diverse hormones. The first one is synergism, and this is when different hormones act together to augment the effect on specific tissues. The second type is permissiveness, where one hormone can't fully exert its full effect without the presence of a second hormone or maybe a greater concentration of a first hormone. There's also something called antagonism, and this is where some hormones oppose the action of other hormones to diminish the first hormone's effectiveness. For example, glucagon and growth hormone both raise blood glucose concentrations to counter insulin's glucose-lowering effect. So what does this have to do with skeletal muscle as an endocrine organ? In 2003, scientists actually discovered small proteins that serve as messengers between cells, and they named these substances cytokines. They were first identified from contracting muscle cells that produced and released substances exhibiting strong metabolic effects. This discovery of contracting muscle as a cytokine-producing organ opened a new paradigm that views skeletal muscle as a hormone-secreting endocrine organ that actually influences metabolism in other tissues and organs. These muscle-secreted cytokines, they're also referred to as myokines, and other peptides produced, expressed, and released muscle fibers exert autocrine, paracrine, or endocrine signaling effects. There's further research that actually supports muscle as an active endocrine organ with a capacity to produce and express cytokines that belong to a distinctly different families. And a muscle's contractile activity helps regulate cytokine expression. And for example, what you can see on here and what's written at the bottom of your slide is the type 1 and type 2 muscle fibers express the myokine interleukin 6. And this exerts its effects locally within specific muscle through activation of the AMP activated protein kinase. So both type 1 and type 2 muscle fibers express this, and it's released in kind of this pulsatile fashion, and it acts peripherally when released into circulation. And within the skeletal muscle, interleukin 6 functions as an autocrine or paracrine manner to increase glucose uptake and also fat oxidation. So during physical activity, its peripheral effect increases glucose production by the liver and lipolysis when transported to adipose tissue. So in essence, myokines help regulate not only skeletal muscle itself, but other organs that are considerable distance away. Oops, sorry. The last thing that I want to say before we move on to kind of a review of hormones, their functions at rest and physical activity, is to talk about kind of the patterns of hormone release. Most hormones respond to some sort of peripheral stimuli on an as-needed basis, but others release at regular intervals during a 24-hour cycle. This is called diurnal variation. Some secretory cycles span weeks, others follow just daily cycles. And these cycling patterns do not pertain to just one hormone category. Assessing pulsatile hormone release patterns reveals information not available from a single blood sample. Patterns of release, amplitude, frequency of discharge really provide more meaningful information about hormone dynamics than a hormone's concentration when it's examined at a single time period. Endocrinology, which is basically what we're talking about today, is the study of hormones and their effects on the body. It is actually a very large up-and-coming area of research in regards to physical activity. Very, very, like I said, up-and-coming, but it's very involved, very difficult concepts if you're not careful to study this information. Nonetheless, this is an introductory course. This is your Intro to Exercise Physiology course. So my job is to kind of break it down and keep it simple for you. And that's why what we're going to do right now is go over some of the important hormones, their functions during rest and during physical activity, as well as specific host to gland hormone responses in regards to training. So we're going to start first with the anterior pituitary hormones. Remember, this is attached to the hypothalamus, which is also attached to the brain. You can see the anterior for this particular slide looks like the back, when in actuality I believe it's the front. Remember, anterior always refers to someone's front side or where their face is facing, and the posterior is always the back side. So I guess this is someone looking off to, I guess, to our right now within the slide. So this is the pituitary gland. It shows its secretions in various target glands and also target gland hormonal secretions. And the pituitary gland consists of distinct anterior posterior lobes, each with different hormone secretions. The gland attaches to the hypothalamus by neural elements that innervate the posterior pituitary. This nerve bundle serves as a conduit for hormone movement from its side of synthesis in the hypothalamus to storage in the pituitary. Located beneath the base of the brain, the anterior pituitary secretes at least 6 different polypeptide hormones and influences the secretion of several others. The posterior pituitary, which is an extension of the hypothalamic neurons, secretes the hormone oxytocin, which acts on breasts and the uterus to stimulate milk production, induce labor and delivery, and also vasopressin, which is considered our ADH. You'll hear about that later in your education, which is the antidiuretic hormone. And it acts on the kidneys to decrease urine output and also to control fluid balance. So something that's very important when it comes to physical activity and helping us maintain hydration and avoid an excess loss of fluid, especially in a state like Florida where it can get very, very hot. The first hormone that we're going to discuss in regards to the anterior pituitary hormones is growth hormone, otherwise referred to as GH or somatotropin. And this particular hormone promotes cell division and proliferation throughout the body. You can imagine this would probably be pretty important for anyone that's interested in putting on some lean muscle mass. This hormone facilitates protein synthesis in 3 ways. It increases amino acid transport through plasma membranes, it stimulates RNA formation, and it also activates cellular ribosomes that increase protein synthesis. Growth hormone the release of growth hormone actually depresses carbohydrate utilization while increasing fat use for energy. If we have an insufficient growth hormone secretion early in life, this can blunt skeletal growth. It can cause dwarfism in individuals. Excess production can produce extreme growth. So maybe something like Marfan syndrome where they have very, very long limbs, or even something like gigantism. Excessive growth hormone secretion after puberty causes continued soft tissue growth, bone thickening, which is a condition termed acromegaly. And many of the growth-promoting effects of growth hormone arise from an intermediate chemical messenger on different target tissues rather than direct action of growth hormone itself. So these peptide messengers, which are produced in the liver, are termed somatomedians, or insulin-like growth factors. You'll hear about that a lot as well, IGFs, specifically IGF-1 and IGF-2, based on their structural similarity to insulin. The liver directly releases IGF-1 and IGF-2 under stimulatory effects of growth hormone, and these factors exert potent peripheral effects on motor units. Hypothalamic secretion of growth hormone releasing hormone stimulates the anterior pituitary gland growth hormone production. Another hormone, hypothalamic somatostatin, inhibits growth hormone release. And this is important to note. Each primary pituitary hormone has its own hypothalamic releasing factor. So anxiety, stress, physical activity provides a neural input to the hypothalamus, causing it to discharge, releasing these particular hormones. And that's why you see the last bullet on this slide here. The growth hormone actually increases a few minutes after physical activity begins, and it's very related closely to peak intensity, more so than duration or total physical activity volume. So again, the secretion increases a few minutes following the initiation of physical activity. Higher intensity activity increases growth hormone production as well as its total secretion. Growth hormone secretion actually is more closely related to peak effort intensity. So in other words, how hard someone's working than actual activity duration involved. So the harder that you work, so if you're someone that's working to max out, if you're working at a very high percentage of your VO2 max, there will be increased growth hormone secretion than if you just simply decided to exercise for 2 hours. The exact stimulus for growth hormone release with physical activity kind of remains unknown. Neural factors most likely provide primary control. One hypothesis maintains that physical activity directly activates growth hormone secretion that in turn then stimulates into anabolic processes. For example, activity doubles growth hormone pulse frequency and amplitude. Physical exertion also stimulates endogenous opiate release. These hormones facilitate growth hormone discharge by inhibiting the liver's production of somatostatin, which is the hormone that blunts growth hormone release. So this is kind of a good graphic to show you what happens as far as the actions and regulation of growth hormone. Thyroid stimulating hormone, or TSH, maintains growth and thyroid gland development, including hormone output regulation from the actual thyroid cells. Thyroid gland plays an important role in controlling cellular metabolism. Usually physical activity increases the anterior pituitary TSH output. Corticotropin. The hypothalamus secretes corticotropin-releasing hormone, is also CRH, into the hypothalamic hypophyseal portal system. Big mouthful there. And it's transported into the anterior pituitary, which then stimulates the release of corticotropin, so ACTH. This then acts on the adrenal cortex to promote cortisol synthesis and release, similar to how TSH controls thyroid secretions. Corticotropin directly enhances triglycerol mobilization from adipose tissue, increases the rate of the gluconeogenesis, and stimulates protein catabolism. Corticotropin concentrations increase again with physical activity duration if effort intensity exceeds 25% of aerobic capacity. Gonadotrophic hormones. These include follicle-stimulating hormones, the FSH, as well as the luteinizing hormone. Specifically in women, FSH initiates follicle growth in ovaries, stimulates ovarian secretions of estrogen, which is one type of female sex hormone. The combination of luteinizing hormone and follicle-stimulating hormone stimulates estrogen secretion and initiates follicle rupture to allow the ovum to pass through the fallopian tube for fertilization. In men, FSH stimulates germinal epithelial growth in the testes, in which to promote sperm development. Luteinizing hormone stimulates the testes to secrete testosterone. Prolactin. This governs milk secretion from the mammary glands. Levels typically increase with higher effort intensities and also return towards baseline within 45 minutes of recovery. Okay, let's talk about posterior pituitary hormones. This gland stores two hormones, antidiuretic, ADH, or otherwise known as vasopressin and oxytocin. The posterior pituitary doesn't synthesize its hormones. Instead, it actually receives them from the hypothalamus for release to the general circulation via neural stimulation. Vasopressin primarily limits how much urine the kidneys produce. Oxytocin stimulates uterine muscle activity as well as milk ejection from breasts during lactation. And this is why oxytocin contributes importantly to birthing and nursing. If you've ever had a baby or been around someone that's had a baby, sometimes they will give women oxytocin to produce contractions or to speed up the rate of contractions in order to aid in the delivery of the baby. Moderate physical activity actually provides a potent stimulus for ADH secretion. The secretion increases kidney tubule water reabsorption during and following physical activity, and the ADH release stimulated by sweating preserves body fluids, particularly in hot weather activity accompanied by dehydration. Thyroid hormones, specifically calcitonin and thyroxine. So the thyroid hormones that are mentioned here are present on the thyroid gland. It's butterfly-shaped, it weighs about 15 to 20 grams, and it's located just below the larynx at the base of the throat. This is a larger endocrine gland. It has two distinct endocrine cell types that secrete calcitonin, which is a calcium-regulating hormone, and then two protein iodine-bound hormones, T4 and T3, which are the major metabolic hormones. So TSH released by the anterior pituitary gland stimulates thyroid gland, and it's released to hormones. So thyroid hormones, ladies and gentlemen, really can affect quality of life. They're not directly essential for life, but they do affect quality. In children, full expression of growth hormone requires thyroid activity. Thyroid hormones provide essential stimulation for normal growth and development, especially of nerve tissues. Hypersecretion of thyroid hormones, which is hyperthyroidism, has four effects. It increases oxygen uptake and metabolic heat production during rest, which causes this heat intolerance, which is obviously a common complaint if you're constantly hot and sweaty. It increases protein catabolism due to subsequent muscle weakness and weight loss. So someone that's suffering from hypothyroidism can't put on lean muscle mass, No matter how much they eat, no matter how much they lift weights, they're typically suffering from weakness and weight loss. Heightens reflect activity and psychosocial disturbances that range from, here we go, irritability and insomnia to even psychosis. So hyperthyroidism isn't a joke. It's not to say that that 3% that's actually suffering from hyperthyroidism isn't a big deal. It is, because being constantly irritable, having issues with insomnia, all the way leading up to something severe, psychosis, is a big problem. Hyperthyroidism also causes an abnormally rapid resting heart rate. We learned that yesterday in terms of calling it tachycardia, which if we have an increased heart rate, our heart is having to work harder, and so that's got some issues with that as well. If we have a thyroid that's not producing enough of the high thyroid hormones, this is considered hypothyroidism, and the 4 effects associated with that are that there is a reduced metabolic rate, which means there's some sort of cold intolerance from reduced internal heat production. We've got decreased protein synthesis. Typically, someone that's suffering from hypothyroidism will have thin hair, maybe lots of hair falling out, maybe suffering from a little bit of baldness, very brittle nails, very dry skin, thin skin, very easily cut, and it's very uncomfortable. They also have a depressed reflex activity, so they have sometimes very slow speech, maybe a very slow thought process, which might cause feelings of fatigue, maybe some sort of diminished mental capacity. And then the opposite of tachycardia is bradycardia. So someone that's suffering from hypothyroidism has a very low resting heart rate. Blood levels of free T4 not bound in plasma protein increase during physical activity. And this could result from core temperature increases with exertion that alter protein binding of several hormones, including T4. The importance of these transient alterations in hormone levels really remain unknown and requires further research by scientists. Attached to the thyroid are 4 small sections of tissue which make up the parathyroid gland. And it secretes a calcium-regulating parathyroid peptide hormone known as PTH. And it increases plasma calcium concentration in 3 ways. Mobilizes calcium from the bone, it enhances renal calcium absorption, and indirectly increases intestinal calcium absorption by its influence on vitamin D. The adrenal hormones are located on the kidney themselves. There's 2 of them, the adrenal cortex and the adrenal medulla. So these are kind of the hormone organs that are referred to as the hats sitting on top of the kidneys, and that's what you see here on this picture. They are flattened cap-like glands located on top of the kidneys. The inner and the outer portions both secrete different types of hormones, and so that's why it's different to understand the difference between the 2. You can see here that the medulla is the inside of the adrenal hormone gland, and this is where the catecholamines and epinephrine and norepinephrine come from. The exterior of the medulla hormone gland is the medulla cortex, and that's where we've got the mineral corticoids that come into play, specifically androgens. Cortisol is a big one in helping regulate sleep patterns. And then aldosterone, corticosteroid, and I'm not even going to try the next one, deoxycorticosteroid. Wow, I think I got that one out. So let's talk a little bit more in depth of the adrenal hormones. So basically the effect comes from the pituitary gland, which stimulates corticotrophin, which then acts upon the adrenal glands, and that specifically is located on top of the kidneys again. So what gets stimulated depends on a couple different things. And one of those things is physical activity. So let's focus on first the adrenal medulla hormones. It does form part of the sympathetic nervous system. It prolongs and also augments sympathetic neural effects by secreting 2 hormones, epinephrine and norepinephrine, which are also referred to as our catecholamines. Neural outflow from the hypothalamus directly influences the adrenal medulla secretions. Up to 80% of it is epinephrine. And this affects the heart, our blood vessels, and our glands in the same but slower way as does direct sympathetic nervous system stimulation. Physical activity intensity directly governs the quantity of adrenal medulla secretion. For example, norepinephrine levels increase 2 to 6 times throughout physical activity gradations from light to maximum. Duration also influences catecholamine response, as revealed by a direct relationship between plasma epinephrine and norepinephrine levels and mileage run. Athletes involved in sprint power training show greater sympathoandrogenic activation during maximal physical activity than counterparts trained in aerobic activities. So this difference relates to higher anaerobic contributions to max energy output during sprint power activities. Other factors that determine catecholamine response to physical activity include age, intensity, duration, as well as gender. Next, we're going to talk about the adrenal cortex hormones. The adrenal cortex secretes adrenocortical hormones in response to the ACTH stimulation from the pituitary gland. There are 3 categories of these steroid hormones by function. They're also each produced in the adrenal cortex zone or also in the layer. And we're going to talk about the mineralocorticoids, the glucocorticoids, and the androgens. Mineralocorticoids regulate mineral salts such as sodium and potassium in the extracellular fluid space. Specifically, aldosterone, the most physiologically important of these hormones, comprises almost 95% of all mineralocorticoids. Aldosterone regulates the kidney's distal tubules' sodium reabsorption. Increased aldosterone secretion moves sodium ions that also draw fluid from the renal filtrate back into the blood, with little sodium passing into the urine. Conservation of fluid via the sodium reabsorption increases plasma volume, often concomitant increases in cardiac output as well as arterial blood pressure. In contrast, when aldosterone secretion ceases, sodium and fluid literally pour into urine for excretion. Chronic reduction in renal blood flow at rest, perhaps from abnormal sympathetic stimulation, activates a renin-angiotensin mechanism. Hypertension occurs from the prolonged over-response to this mechanism with resulting excess aldosterone output. High blood pressure associated with increased aldosterone production often occurs in obese teenagers and is related to 3 factors: decreased salt sensitivity with increased water retention, increased sodium intake, and decreased sensitivity in effects of insulin. This is called hyperinsulinemia. Another adrenal cortex hormone that we're going to talk about is the glucocorticoids, specifically cortisol secretion. This is a major steroid glucocorticoid of the adrenal cortex, and it has some pretty important actions on target tissues. Cortisol secretes with strong diurnal rhythm. Secretion normally peaks in the morning and diminishes at night. Cortisol secretion also increases with stress, so this is why sometimes cortisol is referred to as the stress hormone. The catabolic hormone cortisol counters hypoglycemia, which makes it essential for life. For example, animals whose adrenal glands have been removed don't survive when exposed to significant environmental stressors. Cortisol exerts a permissive effect on hormones. And here are the 6 main effects of cortisol. It promotes liver gluconeogenesis. It degrades skeletal muscle proteins for gluconeogenic substrates. It enhances lipolysis, which is that fat breakdown during low energy intake, and also during prolonged moderate physical activity. It also suppresses immune system function. It promotes negative calcium balance and influences brain function, including mood changes and alterations in memory and learning. Physical activity intensity and duration, as well as fitness level and nutrition status, even circadian rhythms determine cortisol production. Cortisol outputs increases with activity intensity. High cortisol levels occur in prolonged marathon running, long duration cycling, as well as hiking. Plasma cortisol also increases at relatively low levels of sustained activity and can remain elevated for up to 2 hours during recovery. The final adrenal cortex hormone that we're going to discuss are androgens, and these are the adrenal glands and ovaries, obviously in females, the testes in males, which produce sex steroid hormones collectively termed are androgens. And these endocrine gland hormones promote sex-specific physical characteristics, as well as initiate and maintain reproductive function. Remember, this is not distinctly male or female hormones. Rather, androgens exhibit general differences in hormone concentrations between the sexes. Specifically, ovaries provide the primary source of estradiol, which we commonly are aware of as estrogen, and luteal phase progesterone. The adrenal glands in males and females synthesize DHEA and its sulfite DHEAS. The testes produce testosterone, which are also secreted in small amounts by the ovaries. Conversely, testosterone converts to estrogen in the peripheral tissues. So what you can see here in figure 1211, it shows that testosterone, among its many functions, initiates sperm production, stimulates development of male secondary sex characteristics, mainly with facial hair, pubic, and body hair, vocal cord enlargement, and a deepening of the voice. Testosterone's anabolic tissue-building role contributes to the male-female phenotype differences in muscle mass and strength that emerge at the puberty onset. Testosterone conversion to estrogen in the peripheral tissues, under control of the enzyme aromatase, protects male bone structure throughout life. The ovaries provide the primary source of estrogens. Plasma testosterone concentrations in females, which is about 1/10 the level of males, increases with physical activity. So does estradiol and progesterone, however, though. Resistance training and moderate aerobic physical activity increase serum and free testosterone levels after about 15 to 20 minutes in untrained men. Testosterone decreases below resting values during longer duration and intense aerobic activity. Ladies and gentlemen, this is why it is absolutely impossible for females to bulk up similar to how a man would be able to, because of the small, minute levels of testosterone present, and because of the fact that while ovaries produce a minute amount of testosterone, it converts to estrogen in peripheral tissues. So this is a myth that needs to be addressed, specifically within the female population, to help them understand how important it is to resistance train. We go back to the concepts that cardiovascular training is important for your heart. Resistance training is important for the strength of your muscles to allow you to age and still be able to perform the functions that you want to perform. Living on your own, driving a car, being able to sit down and stand up off of a toilet or a chair, or being able to take a shower on your own. So if this is something that you've heard, or someone, a female in your life, has complained about, that they don't want to resistance train because they don't want to bulk up, they physiologically do not have the testosterone presence in their body to become developed like a male. That's not to say, however, ladies and gentlemen, that there aren't exogenous ways for females to bulk up, and that's when you begin to see women take on those secondary male sex characteristics of the increased body hair, facial hair, large vocal cords in their neck, and a deepening of their voice. That is achieved through exogenous testosterone that requires some sort of injection and purchase of extra hormone. It's not something the body can produce. Okay, so I'll get off my soapbox on that because I feel very strongly about females and lifting weights. The next slide is actually showing the cortisol secretion. This is a little bit out of order because we've already talked about cortisol secretion, but nonetheless, this is showing you the examples that the cortisol secretion happens according to the circadian rhythm. So our natural sleep variations, stress that's involved in our daily lives, whether it's eustress or distress, it directly affects the hypothalamus, which increases the CRH secretion, which then affects the anterior pituitary, which then causes more ACTH secretion, and then ultimately the adrenal cortex is affected, and there we have our increased spike of the cortisol secretion. You can see the different tissues that it affects, from the adipose muscle tissue as well as the liver, and the effects on those particular tissues. I'll have to change that for my next presentation. Sorry, that's out of order. All right, next up is talking about pancreatic hormones. Our pancreas is about 14 centimeters long. It weighs about 60 grams, and it lies in the abdominal cavity below our stomach. So you can see in the next slide an illustration of its location, as well as some different endocrine cells associated with it. German microscopic anatomist and physician Paul Langerhans first described the cluster of cells within the pancreas. These accumulation of cells, close to even 1 million, were later named the islets, or islets, however you want to pronounce that, of Langerhans in his honor. They contain 4 distinct cell types, each associated with a different peptide hormone. About 3/4 of the islet cells are beta cells that produce insulin, and a peptide called amylin. Another 20% are alpha cells that secrete glucagon, and the remaining cells include somatostatin secreting D cells and those that produce pancreatic polypeptides. Insulin and glucagon act in antagonistic fashion to modulate plasma glucose levels. The blood usually contains both hormones. The ratio of these hormones present determines which hormone and its action take over and dominate. In the post-absorptive Fed condition, insulin dominates, and the body remains in a net anabolic state. Ingested glucose provides substrate for energy metabolism, and any excess stores as glycogen or synthesizes to fat and protein. In the opposite, in a fasting state, glucagon dominates to prevent low plasma glucose concentrations called hypoglycemia, which means not enough circulating blood glucose or blood sugars. So they kind of act in tandem. The dominating action that takes place really depends on what's circulating within the blood glucose. And this is kind of leading up to our discussion on diabetes. So next we're going to really look at insulin secretion in regards to insulin assisting glucose into our cells. So there are 5 factors that influence the insulin release after we consume a meal. It depends on the increased blood glucose concentrations. Anything greater than 100 milligrams represents the main stimulus to promote insulin secretion. Glucose absorbed from the small intestines and travels to the bloodstream to the pancreas B cells, where a transporter initiates then the insulin release. The next step is an increased blood amino acid concentration. Increased plasma amino acid concentration, which typically occurs after a meal, then triggers the insulin release. Next, we have the gastrointestinal tract hormones. And these are several hormones that are released from the intestinal tract after a meal that travel in circulation to the B cells in the pancreas to stimulate insulin release. 2 of the most important of these hormones are the glucagon-like peptide and the glucose-dependent insulinotropic peptide. And both of these hormones trigger insulin release even before glucose reaches the beta cells. We also have parasympathetic nervous system stimulation. So we have this increase in stimulation of the intestinal region, and the pancreas directly promotes insulin release as well. So not only do we have these hormone effects taking place, our parasympathetic system begins to stimulate the release, as well as a sympathetic nervous system stimulation that inhibits insulin secretion. So during relative intense physical activity, potentially to a stress point, sympathetic input to the pancreas increases to inhibit insulin secretion to stimulate gluconeogenesis. And this provides extra glucose for the nervous system as well as the skeletal musculature. So to kind of break down, before we talk about insulin's functions, let's really break down the glucose-insulin interaction and how this affects the body and why it happens the way that it does. when we consume a meal, we've got higher blood glucose levels that occur within the pancreas, and this is what directly it controls insulin secretion. So we have elevated blood glucose, which triggers this insulin release, and then this in turn induces glucose entry into the cells, which lowers blood glucose out of the blood and removes the stimulus for insulin release. So again, if you're going back to this picture here, we have high blood sugar. This stimulates the pancreas to produce insulin. And once the insulin takes the blood glucose out and deposit wherever it needs to go, typically the working muscle or tissue, then what happens is we've taken this high blood sugar and reduced it to now we're having low blood sugar. And so there's this negative feedback loop where we no longer need insulin because our body has returned to an acceptable blood glucose level, and that slows down or even stops the production of insulin to stop the process. The interaction between glucose and insulin is that feedback mechanism to maintain blood glucose concentration within very narrow limits. Rising levels of plasma amino acids can also increase insulin secretion, but it really depends on, again, what we're eating, what is the sugar content of the food that we're eating, what is the carbohydrate content of the food that we're eating that would spike this production of insulin from the pancreas to deliver it to the working muscle and out of the blood itself. So that brings us to then this next slide talking about insulin's functions. There are 3 primary target tissues for insulin. They are to take it to the liver, the adipose tissue, and the actual skeletal muscle, the working muscle. Insulin's major function regulates glucose metabolism by facilitating cellular glucose uptake in all tissues except for the brain. So without insulin, we would not be able to transport glucose into the cells, and that's a very big issue. And again, we'll talk about that a little bit when we're talking about diabetes. So insulin exerts its action on glucose in 4 different ways. The first way is that it increases glucose transport into most insulin-sensitive cells, not all. Adipose tissue and resting skeletal muscle do require insulin for glucose uptake during rest. Active skeletal muscle does not depend on insulin for its glucose uptake. A second way is that it enhances glucose cellular utilization and storage. Insulin activates enzymes for glucose utilization and glycogen and fat synthesis. Insulin simultaneously inhibits enzymes for glycogen breakdown, glucose synthesis, and also fat breakdown in order to ensure that metabolism moves toward anabolism. That's a breakdown. So consuming more glucose than needed for energy metabolism actually converts excess to glycogen or fatty acids. This is why we need to be very careful and monitor what we're eating and how many calories we're inputting in a day, because if we have extra storages, especially in regards to glucose, and there isn't a need for that excess glucose, then it's actually converted to fatty acids within the body. Another way that insulin exerts its action on glucose is through enhancing utilization of amino acids. Insulin activates enzymes for protein synthesis and also inhibits enzymes that promote protein breakdown. And the final way is that it promotes fat synthesis. Insulin inhibits fatty acid, which instead promotes conversion of excess glucose into triglycerols through lipogenesis. So this illustrates how insulin's anabolic functions promote glycogen, protein, and fat synthesis. With insulin deficiency, the action of glucagon predominates and cells engage in a catabolic activity. Oh, and you know what? I said earlier that anabolism is breakdown. Anabolism is a build up. Sorry. Catabolism is breaking down. So when we say that cells engage in catabolic activity, that's a breakdown. And by the way, if you haven't gotten on your online textbook at the point through your Lippincott website that's posted for you on Blackboard, you're actually able to watch an animation in regards to the insulin functions that we're discussing here. This would be a good point to stop the video and check that out. Next up, we're going to talk about glucagon secretion, specifically when the pancreas and the islets of Langerhans, when they secrete glucagon, it increases blood glucose levels and stimulates liver glycogenolysis, gluconeogenesis, and lipid catabolism. And the blood glucose level regulates glucagon release. So again, our body is constantly monitoring what's present in the blood in order to determine if insulin is needed or if there's a need for glucagon release. Blood glucose level regulates the stimulation if there is a decline in the concentration itself below 100 milligrams per deciliter. And this is what actually stimulates the A cells to release the glucagon. And this is what results in the liver's near instantaneous glucose release. Glucagon contributes to blood glucose regulation during endurance activity, and it's a considerable reduced caloric intake as well, and both conditions markedly decrease blood glucose and then glycogen reserves. Plasma amino acids also stimulate glucagon release. So what are glucagon's functions? The liver represents glucagon's primary target tissue, stimulating glycogenolysis as well as gluconeogenesis to create glucose or increase glucose output. So for example, when we all go to bed at night, we don't eat for 8 hours, 10 hours, however long it is that we sleep. 75% of our glucose produced by the liver comes from our glycogen stores, with the remaining 25% produced from the gluconeogenic reactions. Glucagon also exerts a catabolic effect on adipose tissue throughout the body. So you can see here that when we have this increased glucagon secretion, it affects the liver, specifically the adipose tissue. It increases lipolysis, which is the breakdown, and it also reduces the triglycerol synthesis or creation. And you can see the different effects on the liver as well. Glycogenolysis increases while the synthesis goes down. Glyconeogenesis as well as ketone synthesis increases, and it reduces the amount of protein breakdown in the body. So what does all this have to do with diabetes mellitus? There's actually 4 subtypes. 4 subtypes of disorders that are classified under diabetes mellitus. There's type 1, type 2, there's also gestational diabetes for pregnant women, and then we also have a categorization called prediabetes, where our blood glucose levels are reaching higher than normal levels, but don't actually reach the cutoff number for a diagnosis of type 2 diabetes. It is a category that exists in order to prevent the development of type 2 diabetes, and so that's why it's considered a subgroup. Type 1 diabetes is mostly affecting young individuals. They are born with some sort of failure in their body to produce insulin itself. So typically you're very young when you're diagnosed with type 1 diabetes. We'll talk about the symptoms in just a little bit. Type 2 diabetes usually develops later in life because of lifestyle behaviors that are occurring, such as sedentary behaviors, improper diet, or a combination of both. And this kind of yields a relative insulin deficiency that results in hyperglycemia. Gestational diabetes develops in pregnant women. Typically at a certain point in a woman's pregnancy, they'll visit their doctor's office. They have to ingest a certain amount of drink or beverage, and then they have to wait 2 hours for their doctor to look at their blood sugar levels to determine if they've developed gestational diabetes. Typically, a woman that does develop gestational diabetes over the course of her pregnancy will revert and not have diabetes post-delivery, but that's not always the case. So doctors do want to monitor that very carefully in pregnant populations. And then again, prediabetes. These are for any individuals that are making kind of those poor lifestyle behaviors and choices that indicate they are closer and closer to being actually diagnosed with type 2 diabetes. So typically when we talk about diabetes, we'll hear about type 1 and type 2 forms. Again, type 1 is typically the juvenile onset where it happens. Usually you're diagnosed before the age of 20. Most cases are diagnosed around the age of 12 years old. Actually, there's been a lot of cases within recent years of very young children, we're talking about ages 6 and 7, that are being diagnosed with it. That does require an individual to have insulin injections. It depends on how that's done. Sometimes I know that there's shots for it. I know that there's actually insulin pumps. And so it just kind of depends on the technology and what your insurance can afford. The symptoms are relatively severe if we're talking about hypoglycemia. It's really actually a small percentage of the population when comparing how many individuals have type 1 diabetes versus type 2. If someone typically has diabetes, usually it's someone that's suffering from type 2, it's an adult. Only about 5 to 10% of the diabetic population is diagnosed with type 1 diabetes mellitus. So type 2 is typically referred to as the adult onset diabetes. It's pretty stable. A lot of the symptoms, a lot of the issues with type 2 diabetes can be reversed, not completely erased, but heavily reversed with changes in their lifestyle behaviors. So being physically active, choosing to consume a healthy diet. Mostly type 2 diabetes develops from obesity, so that extra adipose tissue that can cause our bodies to be maybe not as efficient with our insulin as possible. So that's usually how doctors will prescribe. You treat type 2 diabetes. There might be some medication involved, but one of the first things that doctors will say is we need to change your diet. We need to get you to be very physically active. And there may be some medical medicinal intervention as well. Signs and symptoms. You do have a really good kind of checklist in your book that you can go through and check off certain boxes and then check your score to see if you are at risk for type 2 diabetes. As parents, as coaches, as trainers in the industry, these are some signs and symptoms that you need to be aware of that maybe your client or maybe your athletes might complain of that are indicative of diabetes. Hyperglycemia, which means elevated blood glucose. Of course, that's not something that you can just simply look at someone and say, oh, you have elevated blood glucose. That actually requires a blood draw or a finger stick. But other ones such as polyuria, polydipsia, polyphagia, which is using the bathroom consistently, always being thirsty, and always being very, very hungry. Those are signs and symptoms of diabetes. If you have a child that are exhibiting those types of symptoms, you need to go see your doctor. Also, very high levels of blood ketones. Again, this is something that would require a blood draw. If you're someone that has unexplained weight loss, or you're very, very tired all the time or very irritable, again, these are symptoms. If you have several of these symptoms, or if someone complains and you notice they have several symptoms, it's important to get them to see a doctor. So there are actually several tests that can diagnose someone with diabetes. Oh, sorry, there's one more slide too. Blurry vision, numbness or tingling in the extremities, especially for older individuals. If you notice that they're very slow healing wounds or sores, or they constantly have infections and they take very long to heal, again, more signs and symptoms that you need to be aware of, especially if you're someone that's dealing with a special population. Let's say that you do go into the fitness industry and you're working with masters athletes or older individuals, especially maybe in cardiac rehab. This would be good things to look for or listen for when you're having those health history questionnaire conversations prior to exercise. Okay, so before I talk about the tests for diabetes, the other thing that I want to talk about is genetics of diabetes. A simple pattern of inherited characteristics doesn't fully explain the risk of contracting diabetes. So there are two factors that predispose someone to diabetes. If they have some sort of inherited genetic predisposition, or if there are environmental factors that trigger activation. Most type 1 diabetics inherit risk factors from both parents, with inherited traits more common in whites than in blacks or Asians. The most prominent environmental trigger include cold weather exposure, viral infection, and early dietary patterns. It's actually less common in those who are breastfed, in those who first ate solid foods, and also a later age. Disease onset can occur at any age, but the peak age for diagnosis typically occurs in someone's mid-teens. In Western populations, each child has a 0.3 to 0.4 risk of developing diabetes by age 20, and the risk increases 15-fold in siblings of an affected child. Genes in the human leukocyte antigen region on chromosome 6 account for approximately 50% of the genetic risk of type 1 diabetes. And research has shown that chromosome 11, located at a specific region of the insulin gene, contributes about 10% of genetic susceptibility. There are also 40 additional genes that make only a minor contribution to type 1 diabetes mellitus. Type 2 diabetes mellitus has a stronger genetic basis than type 1 because its occurrence really depends more on environmental and behavior factors. A family history of type 2 diabetes represents one of the strongest risk factors for the disease, but only for people living in a typical Western lifestyle. And so that's where we live. Our diets consist of a high-fat diet, a low intake of complex carbohydrates and fiber, also paired with inadequate physical activity. Overfatness provides a considerable risk factor for developing type 2 diabetes. Diabetes-prone individuals possess a gene that directs synthesis of 3 mitogen-activated protein kinases that inhibit insulin's action in cellular glucose transport. The peak age of developing type 2 is usually much later than life than type 1. African Americans, Mexican Americans, and Pima Indians have the highest risk for developing type 2 diabetes. And so the disease results from 5 complex physiological processes. The pancreatic B cells, peripheral glucose uptake by the muscle, adipocyte release of multiple cytokines and hormone-like molecules, hepatic glucose production, as well as influence from the central nervous system. So there are 3 specific factors that can produce high blood glucose levels in patients with type 2 diabetes. An inability of the pancreas to produce sufficient insulin to control blood sugar. So this is typically referred to as insulin deficiency. Decreased insulin effects on the peripheral tissue, which is called insulin resistance. And then you can also have a combined effect of both factors, 1 and 2. Okay, so now we're getting back to the tests for diabetes. There are several tests to diagnose diabetes. The American Diabetes Association recommends a fasting plasma glucose test rather than a popular oral glucose tolerance test. This particular test evaluates blood sugar levels 5 times over a 3-hour period after drinking a glucose-containing solution. And then the fasting plasma glucose test measures plasma glucose following an 8-hour fast. The current value for suspected diabetes is now lower than the previous 400 milligrams per deciliter standard. So this acknowledges that patients can remain asymptomatic with microvascular small blood vessel damage with the fasting plasma glucose values in the low to mid, even 120 milligrams per deciliter range. So if you're someone that does the FPG assessment and you have a greater than 126 milligrams per deciliter value, you're diagnosed with diabetes. There's an additional assessment. It's very commonly referred to as the A1C test or the HB1C test, and this actually quantifies how much hemoglobin has been coded over a 3-month period. So this looks at the amount of glucose attached to the bloods in the red blood cells. So the cutoff for diagnosing pre-diabetes range between 5.7 to 6.4, and then above 6.5 for actually diagnosing someone with type 2 diabetes. The tests that show you your A1C levels show that individuals with a higher than normal A1C levels are at increased risk of developing type 2 diabetes, as well as heart disease and stroke. Studies of individuals at high risk for diabetes show that lifestyle intervention that resulted in weight loss and increased physical activity can prevent or even delay type 2 diabetes. In some cases, not all, blood glucose levels were even returned to the normal range. So this is why individuals that are either at pre-diabetes or have been diagnosed with type 2 diabetes are always prescribed by their physician to alter their diet and to increase physical activity in order to affect these A1C levels and to reduce them. Currently, 37% of U.S. adults ages 20 years or older had pre-diabetes. 51% of those aged 65 years or older were also categorized as having pre-diabetes. The next portion of your slide then discusses metabolic syndrome. This is a multifaceted group of coronary artery disease risks, defined with 3 or more of the criteria listed for you here. This is a disease of the modern civilization. It affects millions of adults in the Western industrialized countries. It's much more common in men than in women. The disease occurrence actually relates to genetic, hormonal, and lifestyle factors, specifically obesity, physical inactivity, nutrient excess, including higher than desirable intakes of saturated and trans fatty acids. The clustering of insulin resistance and hyperinsulinemia characterizes metabolic syndrome. Any individuals with these prominent characteristics are at higher risk for coronary artery disease and should receive appropriate attention and treatment. So what is it? It is a common condition that includes obesity, high blood pressure, high blood glucose, and an abnormal cholesterol profile. This syndrome affects 25% of adult Americans. And the chance of developing coronary heart disease or stroke and diabetes increases when these risk factors cluster together significantly more than when risk factors develop independently. So this is done in kind of your pre-assessment when you're meeting with clients. And another reason why we look at the risk classifications and stratifications to determine if they have a number of these symptoms, being, again, obese, having high blood pressure, high blood glucose, and abnormal blood lipids or dyslipidemia. So it's actually pretty common. If you've got someone that suffers from one of those things, they're probably on their way to suffering from metabolic syndrome. Talking about metabolic syndrome, a couple different risk factors in regards to their waist girth. This is an assessment that we do taking waist circumference. Men that have a waist circumference of greater than 102 centimeters, women more than 88, have are at increased and great risk for abdominal fatness or suffering from abdominal fatness. Again, you can see the cutoff point for the triglycerides as well as the lipoproteins, blood pressure, and fasting glucose. So this would require someone having some sort of blood draw with a physician, and then probably a return visit to read those values and to interpret them and to discuss the possibility of disease development and how it relates to any genetic, hormonal, or lifestyle factors, like we talked about earlier, obesity, inactivity, excess consumption of nutrients, and then these high intakes of saturated and trans fatty acids. In regards to diabetes and physical activity, this hypoglycemia during physical activity is common disturbance of the glucose homeostasis for anyone suffering from type 1. So this means that we need to keep a very watchful eye on individuals that we are aware of that suffer from diabetes and that are going to be very physically active, or at least moderately physically active, under our watch. And that's because of the effects that you see present on this slide. During prolonged moderate effort, hepatic glucose release doesn't keep pace with an increased glucose utilization in the active muscle. Severely reduced plasma glucose should be a concern in patients who require intensive insulin therapy throughout the day to normalize blood glucose levels. So what does this mean? Training for people with diabetes is complex, despite a clear association between regular physical activity and improved insulin sensitivity by the peripheral tissues. We as trainers or people that are supervising exercise programs need to be aware and continuously monitor the exercise of these individuals that are receiving our programming or receiving our training. And the reason is because of an increased insulin sensitivity and fast delivery of injected insulin through more rapid circulation due to physical activity that accelerates glucose removal from the plasma, potentially inducing serious hypoglycemia and then diabetic shock. So what do we have to do? We have to be careful that they have some sort of snack with them. We have to make sure that we're aware of what they ate before they got to the training program. How soon before their session did they eat? What types of foods did they eat? Things like those. In regards to physical activity benefits for type 2 diabetic patients, regular physical activity provides a non-pharmacologic therapy for individuals. And so regular physical activity is diagnosed, if not recommended, for type 2 diabetics. And the reason being is because of the improved glycemic control, the improved cardiovascular functioning, as well as concomitant body composition improvements, as well as psychological profile, and that it can reduce this broad array of risks for heart disease that would cause us to also fall under someone suffering from metabolic syndrome. So here are some of the disease risks, physical activity risks for anyone, whether it's type 1 or type 2 diabetes. The potential problems are listed for you on the right, as well as the system that's affected on the left. Systemic issues that could arise is retinal hemorrhage, increased proteinuria, which means there's an excess of protein in the urine. That's not supposed to happen. That's a bad thing. Acceleration of microvascular lesions can occur. And cardiovascular systemic issues could be arrhythmias, ischemic heart disease, excessive blood pressure, post-exercise orthostatic hypertension. Guys, despite all of these risks that you see here, doctors and physicians still recommend exercise and physical activity for diabetic individuals because the benefits outweigh these risks. In regards to endurance training and the endocrine response, now we're sort of getting away from talking about metabolic syndrome and diabetes and really, again, focusing on the endocrine response to endurance training. We're also going to get into the specific hormones again and how they affect not only endurance training but also resistance training. And that will kind of wrap up the last portion of our lecture. So few studies have evaluated changes in hormonal response to systematic alterations in the frequency, intensity, and duration of physical activity. Most of what researchers know about changes in hormonal dynamics with training comes from studies in which hormone assessment occurred secondarily to other variables. Nevertheless, a picture has emerged of the integrated response of different hormones to training, particularly fluid balance, energy modulation, glycemic control, cardiovascular dynamics, as well as growth and development. Endurance training generally decreases the magnitude of hormonal response to a standard activity level. Physical activity at a particular absolute intensity produces a lower hormonal response in trained subjects than in untrained counterparts. Adjusting intensity to the same percentage of each person's maximum capacity eliminates the trained-related differences in hormonal response. With maximum effort, trained subjects have a similar or slightly higher catecholamine and pituitary hormonal response than untrained individuals. So let's talk about the anterior pituitary hormones in relation to training. Most research regarding growth hormone involves responses to a single physical activity session. Less information exists on growth hormone levels during a prolonged training period. Understanding the dynamics of growth hormone secretions with chronic physical activity takes on significance because of the causal relationship between growth hormone availability and maintenance of fat-free body mass with aging and with weight loss. The graph that you see here looked at long-term training in regards to growth hormone production. And so we're looking at growth hormone concentration during a 20-minute constant load exercise and then a 45-minute recovery at pre-training, as well as 3 and 6 week training. And what we found was that integrated growth hormone concentrations during physical activity plus the recovery period averaged 45% lower than pre-training values at both training measures. Corticotropin, the ACTH, stimulates the adrenal cortex and increases fat mobilization for energy. Training increases the corticotropin levels during physical activity, and this enhanced fatty acid oxidation spares muscle glycogen, which benefits prolonged intense exercise performance. As far as prolactin, it really remains unclear whether long-term training alters prolactin release, other than the training-induced changes mediated by the sympathetic activity or other multiple hormone interactions. In regards to the follicle-stimulating hormone and the luteinizing hormone and testosterone, regular physical activity depresses reproductive hormone responses in men and in women. Women with a history of exercise participation have altered their follicle-stimulating hormone and luteinizing hormone levels, even at different menstrual cycle phases. And these hormone alterations often relate to menstrual dysfunction. The FSH levels decrease in trained women through an abbreviated and an ovulatory menstrual cycle, where the luteinizing hormone and progesterone concentration increase in the cycle's follicular phase. 5 factors other than acute and long-term physical activity can also alter reproductive function in female athletes. We can see weight loss, we've seen dietary changes, which affects their body's lean to fat ratio, as well as the emotional stress of training and competition, as well as altered clearance rates of those gonadal steroid hormones. As in regards to the posterior pituitary hormones, as far as the antidiuretic hormone, we've got maximal exhaustive physical activity at the same relative intensity produces no different in ADH response in trained and untrained individuals. ADH concentrations decrease with training in response to submaximal physical activity with regard to the same absolute intensity. Oxytocin combined with vasopressin increase following prolonged intense endurance physical activity. And the thyroid hormones, exercise training coordinates the pituitary thyroid response that increases turnover of the thyroid hormones, and this is a response usually associated with excessive hormonal action that leads to hyperthyroidism. No evidence, though, indicates that hyperthyroidism develops in highly trained individuals. Basal metabolic rate and resting core temperature often remain normal with training. There is increased T4 turnover, which accompanies chronic physical activity, and this occurs through a mechanism that differs from the hormonal's normal dynamics. In regards to aldosterone, the renin-angiotensin-aldosterone system contributes to the homeostatic control of body fluid volumes, electrolytes, blood pressure, but physical training does not affect resting levels of these compounds or their normal response to physical activity. In regards to cortisol, plasma cortisol levels increase less in trained than in sedentary subjects. Greater cortisol output among untrained individuals may partly result from heightened psychological stress that is experienced during exercise testing. Remember, elevated cortisol levels promotes fatty acid and protein catabolism in order to provide fuel for energy and substrates for tissue repair following exertion. Our catecholamines, epinephrine and norepinephrine, rather than this typical adrenal gland response. See if their graph is following. Yes, so we have an important aspect of the catecholamine response to physical activity involves our sympathetic response from our catecholamines. So you can see here we've got norepinephrine and epinephrine response during physical activity at intensities that range between 60 to 85% of aerobic capacity. Plasma norepinephrine levels increase progressively with intensity before and after training. Training produced higher plasma norepinephrine levels, particularly at higher intensities. Consistently, higher epinephrine values also emerged following training, but the differences did not achieve statistical significance. So this training response reflects three factors that require greater sympathetic nervous system activation from increased activity. Greater absolute demand for substrate use via glycolysis and lipolysis, increased overall cardiovascular response through cardiac output, as well as larger muscle mass activation. In looking at the pancreatic hormones in regards to physical activity, specifically insulin and glucagon, endurance training maintains plasma insulin and glucagon levels in physical activity similar to values at rest. In essence, the trained state requires less insulin at any stage from rest through light to moderately intense physical activity. And there are two mechanisms that help explain the reduced hormonal response to training. The first is an increased muscle and fat tissue sensitivity to insulin, as well as an increased percentage contribution of fat catabolism for fuel during submaximal activity. So this is a schematic model of how heavy resistance training produces favorable adaptations in muscle structure and maximal strength performance when we talk about resistance training and endocrine function. Muscle remodeling with resistance training really reflects this complex process involving a cell receptor interaction with specific hormones, which then stimulates the DNA synthesis of contractile proteins. There is large variation among individuals in muscular strength and gains in hypertrophy, even with similar resistance training programs, and this suggests that there are considerable differences in endocrine dynamics with chronic muscle overload. And last but definitely not least, in regard to the opioid peptoids in regards to physical activity, research in the early 1970s provided first direct evidence that endogenous substances behaved like opiates. So when we get to the 1980s, then researchers discovered groups of endogenous opioid compounds. Now we call them endorphins that bind to families of receptors. So by definition, the term endorphin characterizes a group of endogenous peptides whose pharmacologic action mimics those of opium and its analogs. So not to get too technical with you, endorphins are these group of peptides that can also regulate menstruation. They can regulate other hormones, including ACTH, or catecholamines, as well as cortisol. And the training effects of the endorphin response really remains controversial. There needs to be more research done on it because of the various results that have been produced by the research. And one of the reasons is because it's been proposed that there's a possible effect of training that augments the endorphin and lipotropin release during physical activity. That is our lecture for our hormones, physical activity, and exercise to training. Thank you for listening.